Welcome. Here we're going to calculate the magnetic field inside a toroid using Ampere's law. Now, a toroid is essentially a really fancy word for the same geometric shape of an everyday common glazed donut. So to make a toroidal magnetic field, we could imagine taking a wire and winding that wire around the donut some number of times. And we would be careful to make sure that that wire is wound in the exact same direction every time. So all of those loops of wire, the current, if it happens to be coming in this way, would be going into the board at the center of my donut and coming out of the board along the edges of my donut. Now, Ampere's law tells us if we want to calculate the magnetic circulation, the integral of the magnetic field dotted along some path, that's going to equal mu naught times our current enclosed by the Amperian loop traced out by our path. So, if we take a look, we can split this donut into three regions. Region 1 is just inside the center. Region 2 is in the donut part of the donut. And region 3 is outside the donut. So in the whole, everything here is circularly symmetric, so I could just imagine drawing a circle centered at the center of my circle. Well, if the radius of my Amperian loop is smaller than the inner radius of that donut, I don't enclose any of those wires. So according to Ampere's law, my total circulation has to be 0, so the easiest solution, the magnetic field inside, is going to be 0. Now, outside, if I were to, again, use circular symmetry and trace out a circle around the outside of that donut, then what I would find is for every loop of wire on the outer edge coming out of the board, I would have the exact same number of wires going into the board. And in terms of current, those two directions are exact opposites. So if I have positive number of loops times the current minus the number of loops times the current, I get 0 once again. So outside a toroid, inside a toroid, center, inside the hole, I get 0 magnetic field. So the interesting part is the donut part of our toroid. So if we want to take a look at Ampere's law, again, as I've said twice now, we're using circular symmetry. So if I start at the center and trace out a circle of radius r, well, from symmetry, if all of those loops are all evenly spaced, I would expect the magnetic field to be doing something symmetric. Now, if I use my right hand rule and point my thumb into the board for the direction of that wire right there, well, my magnetic field would be circulating clockwise around that wire. All of those wires would all have clockwise circulation. That means I would expect my magnetic field to be circulating clockwise around this loop as I've drawn it. So if everything's circularly symmetric, my magnetic field should be uniform because of that symmetry. So the integral of my magnetic field along that path is just the strength of my magnetic field times 2 pi times the radius. And from Ampere's law, that's equal to mu naught times the current enclosed. Well, here, the current enclosed depends on how many loops. But for every time I wrapped that wire around my donut, I added a loop of wire going into the board at the very center of this donut. So my total current enclosed is just the total number of loops around my donut times the current in my wire. So setting those two pieces equal to each other, the magnetic field that we get inside a toroid is equal to mu naught times the number of loops of that toroid times the current in my wire divided by 2 pi times the radial distance I am away from the exact center of my toroid as long as I am on the plane of the toroid. Thank you for watching.